everyone, and welcome to the March General Meeting of the Kalamazoo Astronomical Society. It is fantastic to have such a large crowd. We are currently at 95 participants, and I'm sure we'll get a few latecomers here soon. And we do even have a handful on YouTube as well, but we don't need the YouTube yet, but we'll keep it running in case we max out here. So let's introduce our speaker right away. So I first saw tonight's guest speaker give a presentation at Alcon 2017 in Casper, Wyoming, right before the total solar eclipse. And I've been meaning to invite her to speak at a KS meeting for some time because it was such an excellent presentation. So she was born and grew up in England. She studied physics and geophysics at the University of Lancaster. In 1976, inspired by NASA's missions to Mars and the prospect of the Voyager mission, she moved to the US for graduate study at MIT. Her 1981 PhD thesis involved analysis of data from the Voyager Plasma Science experiment in Jupiter's giant magnetosphere. She spent 1982 to 1987 as a postdoctoral researcher in space physics at Imperial College, London. The Voyager flybys of Uranus and Neptune brought her back to the US, and she joined the faculty at the University of Colorado, Boulder in 1989. She is professor of astrophysical and planetary sciences and research scientist at the Laboratory of Atmospheric and Space Physics. In 2015, she stopped teaching in order to have time to focus on Pluto and Jupiter. In addition to the Voyager mission, she has been on the science teams of the Galileo mission to Jupiter and Deep Space One, the Deep Space One mission to Comet Borrelli. She edited Jupiter, Planet, Satellites, and Magnetosphere from Cambridge University Press that came out in 2004. She heads the plasma teams on the first two New Frontier missions, the New Horizons mission, that after a 9.5-year flight flew past Pluto on July 14, 2015, and Juno that went into orbit over the poles of Jupiter in 2016. And I'm pretty sure it was Juno that she spoke about in 2017. So without further ado, please welcome Dr. Fran Bagenal.
Okay, great to be with you. It's a great pleasure. I love talking with Astro Clubs. They're the best people to talk with. I love it. Okay, so I am going to share. I'm hoping you can hear me and you can see my presentation. And how about we go with this? Is this now working?
Yes, it is.
You're good to go.
Great. Hide floating meeting controls. I think I can do that. Good. Okay. So, oops, let me do that again. Won't take a second. This is a new feature of Zoom that I've just learned. So I'm going to talk about exploration of the outer solar system. And I'm going to start off with Voyager, my heritage, or the first mission that went out through the outer solar system, talk a bit about New Horizons, and as well about Juno, that is in orbit around Jupiter. And if you like, we can talk more about future missions. I'll throw out a few ideas, and I look forward to discussion in the Q&A about possibilities. So let's start with, the outer solar system. So what we're talking about is Jupiter, Saturn, Uranus, Neptune, and the Kuiper Belt. And we're going to discuss how we've explored these over the past 40 years or so. And of course, Voyager is the great first explorer that went out and went and explored these planets, and is still operating, still working, now outside the interplanetary medium influenced by the sun and out into the interstellar medium. We can talk about that too as well, if you like. Now, I came over to the US after finishing up at the University of Lancaster in the physics department in 1976. There's me at the back. And it just, the 70s, you have to just look at these bell bottoms. The clothing was just hilarious. not to mention the haircuts, but that was the era. And I arrived in America. And, you know, 1976 was a really interesting time for a Brit to arrive in America, because, of course, in the US, and particularly in Lexington, where I happened to be living at the time, they were having a big celebration of the fact that they'd kicked all the Brits out of the country. It was fun, very entertaining. Anyway, good time to come and visit. And it was also good timing because the Voyager 1 and Voyager 2 spacecraft were about to be launched. The following year they were launched and they were sent out going past Jupiter and Saturn. And then Voyager 2 went on to Uranus and Neptune. So fantastic opportunity to explore for the first time these outer planets. This was a fabulous picture of Jupiter taken by Voyager 1 with Io and Europa in the picture with the beautiful great red spot and the clouds behind. And this is a zooming in on the great red spot and all the turbulence, and everyone was going, whoa, whoa, this is amazing, because we really didn't get this sort of view from Earth with Earth-based telescopes. We also got to look at Io, Europa, Ganymede, and Callisto. These are the 4 Galilean moons, sort of the size of Earth's moon, a little bigger. So Io and Europa are about the size of Earth's moon. Ganymede is the largest moon in our solar system. Callisto is a little smaller. These are really interesting environments, which we really got a first close-up view with Voyager as to what these things really look like. But of course, in those days, the technology was pretty crude. We were using punch cards, and I did my thesis work working with punch cards and magnetic tapes and using machines, a bit like the one that this chap is wearing. I didn't wear a suit, of course. And we analyzed the data, and the images came down. They were very slow. They were on the TV. We could get to look at the pictures on the TV, and the data that we analyzed tended to come on these inkjet printers, very slow printing out the data. And here is me working at these very crude keyboards that we had. This is at MIT in one of the labs where I was writing up my PhD. So in 1980, we had Saturn explored by Voyager 1 and Voyager 2. 1986, we had Uranus. And yes, it was a bit of a disappointment. You look how boring it is. Oh, sorry. Uniform it is in distribution, very interesting compared with the other planets. And then 1989, we had this flyby of Neptune with this intriguing feature, this great dark spot, not too different from the great red spot on Jupiter. What's going on? Why are these planets so different? What are the similarities? And so on and so forth. So this really provoked an era of planetary exploration, planetary science, and there was a whole generation of planetary scientists who came out of this era. Now, by Neptune, I actually had a faculty job and taught at the University of Colorado. And I, of course, brought Voyager to the classes and showing them how exciting this was to explore the outer solar system. So if you want to see the whole business of putting together the Voyagers and what happened with the Voyagers, I encourage you to see the farthest. It's now, I don't think it's still on PBS, but you can go watch it, I believe, online and see this whole story. It was a really great documentary put together by a group, an Irish film director, which is great fun. So go check that out. It's good fun. So I want to move on from Voyager to New Horizons. So around the time of the end of Voyager flying past Neptune, and everyone thought, oh my golly gosh, this is the end of solar system exploration. What are we going to do? But as Alan Stern, who was a graduate student at the time, came to me as a faculty member at the University of Colorado and said, hey, we have to go to Pluto. And I was thinking, Pluto? Pluto is so small, so boring. Who cares about Pluto? But he convinced me that there are interesting things to do at Pluto and that we should propose a mission. Now, it was hard to get a mission to Pluto because, again, a lot of people thought Pluto, who cares about Pluto, little planet. But what was interesting is that over time, it got to be a really interesting planet because it was the example of the Kuiper Belt. And we wanted to go look. We knew many, many other objects now out in the Kuiper Belt. And the idea was to go and explore Pluto as an example of the Kuiper Belt. So let me give you some sense of scale here. Earth, obviously, in the middle. And then Pluto and Charon. Now, these are not only to scale in size, but they're also to scale in distance. Okay. And then also above is the numbers in mass. So the Earth is 457 times the mass of Pluto. And Pluto is actually has a really big moon, Charon, which is only 1/8 of the mass of Pluto. So this is really almost like a binary planetary system, small planetary binary system. Now, we designed a spacecraft that would have a bunch of instruments and fly out to Pluto. And it has some obvious major features. It's about the size of a small piano, okay? A baby grand, if you like. It has radioisotope thermoelectric generators, a radioisotope power system. It has a communication with the Earth, and we use this communication with the Earth to do radio science. We call that REX. We had various spectrometers, a UV spectrometer we called Alice, a wide angle camera called Ralph, Laurie, a long range sort of zooming in instrument called Laurie. We had a couple of particle instruments called Pepsi, high energy particles, and SWAP, lower energy particles. So they were measuring the solar wind and the charged particles interacting with Pluto. And then, most important, we added the student dust counter. So the student dust counter was designed, built, tested, operated, and the data analyzed by students at the University of Colorado here in Boulder. And we have now had 8 generations of PhD students who have got their PhDs on data analyzed from the New Horizons student dust counter. It was indeed built by students, and the woman in the bottom left is now actually a mission manager here at LASP. And these other scientists, of these students have all gone on to careers in space science and aerospace of one kind or another. So here is launch day with the students. Here's me on the right with all the students ready for launch. It got launched in January 2006. But of course, it took a long time to get out there. But in the meantime, around the time of launch, in fact, Hubble discovered 4 more moons, Hydra, Nix, Kerberos, and Styx. And so we now had 6 objects to study on the flyby. It took 9.5 years to get there. Yes, it's a long way out there. It takes a while to get there, even if you get a gravity kick at Jupiter, as we did in 2007. But 33 AU is a long way to go. But we measured the solar wind on the way. We tested the instruments, got ready, and we arrived. And the plan is this: we're going to fly through this system, take pictures of Pluto and the 5 moons, and then we're going to do a solar occultation, Earth occultation, make all sorts of observations. But this whole business only lasts about 4 hours. Okay, 9.5 years to get there, 4 hours of data, moving really fast. And because we're so far away, we've got a 4.5 hour one-way communication. And the amount of communication we can do is about 3 kilobits per second transmission. So, you know, your average cell phone right now is a few megabits. So, you know, this was doing our best at the time to send things back, remembering that this spacecraft was built 10 years earlier. And so the technology, things have changed, and it's hard to communicate over 33 astronomical units. So the thing is that if you're that far away, this is a robot, and you have to program it, tell it what to do, make the observations. So you have this saying, okay, observe this moon, observe the planet, go and look at the other moon, go and look at that one, make a different orientation, different view, so on and so forth. So you tell the spacecraft exactly what to do. It is a robot. You give it instructions, it has to do what it's told, and when it's done, then it turns back to the Earth and tells us what it saw. So in the meantime, what do you do while you're waiting for the data to come down? We took selfies. Anyway, here is a really cool picture of the New Horizons team on the day where we were indeed waiting for the data to come down. And this is actually the women. They're about a quarter of the team were women. And we have in here the deputy project scientist and the mission operation manager and all sorts of people playing key roles, as well as those of us who are scientists on the team. So there's an interesting contrast between July 1969, when, of course, the successful arrival of the moon led to these guys who were in the control center celebrating. Notice they were smoking cigars and wearing suits with ties and all this sort of stuff, versus the situation in 2015, when our mission operations manager, nicknamed Mom, Alice Bowman, announces that the spacecraft, that is New Horizons, is all well and full of data, ready to come back. And of course, the team, we began to see these unbelievable pictures of Pluto. And what we see is this icy world with a heart. Now, this is the heart here. From a distance, it looks like a heart, a little less once we get up close. And we all celebrated and enjoyed the fact that we actually had data that were coming down. So these things are really extraordinary, these pictures. I was not expecting anything like as complex a surface. I thought it'd be kind of a little boring, you know, a bit like our moon. I shouldn't say that, it's a bit unfair. You know, what we're seeing here is an amazing structure that has rock in the center, a big layer of water ice and frozen nitrogen on the outer layers. Now we know that it's mostly frozen, this outer layers. But what's interesting is when we look at the actual surface, we see that frozen nitrogen and CO and methane are much more liquid in that they flow more easily. They're still solid, but they're more like, you know, mayonnaise or something like that flows, right? Whereas the water ice on the surface is extremely rigid and strong, almost like rock. And so the mountains are made out of water and the glaciers are made out of these ices. Now, there is some thought that maybe underneath this thick layer of ice on the outer, there may be a thin layer of water, but it's very deep down. And to be honest with you, I don't think everybody was getting excited about possibility of liquid water, thinking about life, but it's so deep down, it's unlikely that there's anything much down there. And we certainly are not going to be able to get down there easily with the spacecraft. So let's think about nitrogen ice. We actually looked at these surfaces and thought, what are we looking at? And it kind of looks like a pot of soup that is turning over, stirring up. It looks like we have convecting nitrogen ice. And then in between, on various places, we see bits sticking up above this nitrogen ice. And we think these are water ice. And they also have some brown stuff on them. What could this be? What could be happening here? So the idea is that you actually get convecting cells of nitrogen, and below we have a sort of simulation of these cells. And these cells of convecting nitrogen ice produce these features up on the left with fresh ice on top, turning over, and the interactions between the cells, giving these lines, these outlines here. And sometimes chunks of water ice are being brought up in these regions in between. So this is very different from anything we've seen in the inner solar system, completely different geology. Similar in some ways to some of the things we see, but instead of rocks and convection with magma, what we're seeing here is ice. It's water ice or nitrogen ice. Then comes the question what the brown stuff is. Now, what we think is that solar ultraviolet light interacts with methane in the atmosphere and makes hydrocarbons. And these hydrocarbons rain down onto the surface. And so there are areas that are very old, like this structure over here, where a lot of these dark, this material, we call them tholins. This was something that Carl Sagan worked on, thinking about UV light and changing methane into hydrocarbons. He was thinking about prebiotic life, but out here at Pluto, it's not prebiotic, it's way too cold. But you're getting this brown gunky stuff, which is sort of like oil that rains out of the atmosphere. On the other hand, there are fresh areas like Tombaugh Regio, Clyde Tombaugh being the discoverer of Pluto back in 1930. These fresh areas, fresh ice, are white and sort of clear ice. Now we look at this picture, this passing picture as we were leaving Pluto, and I have to say, doesn't this look like a planet to you? Really beautiful, where we have the ice, the glacier here, we have mountains, these are as big as the Rocky Mountains, of water ice sticking up, and then we have haze layers of hydrocarbons in the distance. And this is just my favorite picture of Pluto that was taken as we were leaving with New Horizons. So let's jump forward to Jupiter and think about, instead of one of the smaller dwarf planets of our solar system, the largest giant planet of our solar system. So this Jupiter has a mass 318 times the mass of the Earth, and it's 11 times the radius. So you're probably used to seeing these belts and zones and the great red spot. This is actually taken by the Cassini spacecraft as it flew by, but you will see something fairly similar in a fairly good telescope that I'm sure many of you have taken pictures of Jupiter. Now, when we look at this Cassini flyby movie, what we see here is the equatorial region with belts and zones going in opposite directions. We see the great red spot going around. We see these little eddies in various places. Lots of structure in the atmosphere, but we don't see the poles because Cassini was flying on its way to Saturn, getting a gravity assist at Jupiter, and it did not get to see the poles. Now, the big question is, what is going on? What are we looking at when we look at these clouds? What we're actually seeing are ammonia clouds. Okay, not water clouds, ammonia clouds. And they're colored in some way by some materials. And it's not clear what those materials are. You can have really quite small amounts of material causing a lot of coloration. So think about when you bake a cake and you want to add a little coloring to make some frosting that's pink or green or whatever you want to make to celebrate whatever occasion it is with your cake, then you add a drop of coloring to a bowl of icing and it turns the color, right? Same thing with these clouds. You have just a drop of these colorants that affect the clouds and give them these colors. Okay, so we don't have, we're struggling with working out what they are because there's quantities, the concentrations are so low, it's hard to measure what the actual colorants are in the atmosphere. But we do know that the outer layer of the clouds is ammonia clouds. We can detect this using spectroscopy of the atmosphere with Earth-based telescopes. Then below that, we believe there's a mixture of ammonia and sulfur, and you get ammonium hydrosulfide. which is this NH4, CH, SH. And then below that, we think is water. So we think there's a water cloud below this. And this is pretty important. So the reason why water is important is that our theory of how the gas giants formed is that there was, when we look at the solar system and look in the middle bit, we had a new sun, and away from that new sun, where it was hot, it cools off away, and at some point, you get rocks and metals that condense out to make the rocky planets of the inner solar system, Mercury, Venus, Earth, and Mars. And then beyond some point, what we call a frost line, then beyond that, you get frozen hydrogen compounds of water, ammonia, methane, but particularly water. And so you have a lot of, there's a lot of oxygen in our solar system. It's the third most abundant element in the universe. And so we expect that there's a lot of water beyond this frost line that will make the cause of the gas giants. And so once you get a lot of ice, a lot of frost coming together, something like 20 Earth masses, then you pull in the hydrogen to make the gas giants. And so this is our idea, this is our theory about solar system formation and how we make the gas giants. So that's the theory. And what we wanted to do with the Juno mission is to go out and explore and test these ideas by looking at Jupiter in detail, trying to understand the interior, trying to understand the atmosphere. And so we sent out this spacecraft, and just to give you some sense of the scale, at bottom left here, we have a human for scale. We have these big solar panels. It has a, oops, let me go back, a diameter of about 20 meters, so about 60 feet. These are really big solar panels. The power generated is about 500 watts. So think of 5 light bulbs. That's not a lot, but it's enough to do what we need to do. And this whole system is spinning every twice a minute, so every 30 seconds, keeping the radio antenna pointed towards Earth. Okay, so this radio antenna we use for communicating with the Earth, but we also use it for gravity science, and I'll explain that in a minute. We have the end of our solar panels, a magnetometer that measures the magnetic field, the local environment, and we put it as far away from the spacecraft as possible because the spacecraft has electrical currents that generates its own magnetic field, and we don't want to measure the spacecraft magnetic field, we want to measure the ambient one. So we put the magnetometer as far away as possible from the spacecraft. Then we add on some energetic particle instrument, JADE and JEDI, great names, eh? And then we have waves, which measures the radio waves, the plasma waves. And then we have some spectrometers. And we have an infrared spectrometer that was actually built, it's called GIRAM, built in Italy. We have the UV spectrometer that was built in Texas. And we have the microwave spectrometer that goes on the side. And then we have a camera, Juno Cam, that was put on to take pictures. Okay, so this is the spacecraft. This is how it is oriented. And then this is the orbit of the spacecraft, the Juno orbit. So we wanted to get in close to the planet to measure things up close. But that's difficult because on either side, there's this big donut around Jupiter of energetic charged particles. And we've known that because of other spacecraft that have flown by and because of ground-based radio observations that tell us that there are these really nasty million electron volt electrons that are trapped in the magnetic field. We don't want to go there because it's really nasty for the instruments on the spacecraft. So we decided to go over the clouds and underneath the radiation belts, and but to do that we had to go over the poles like this. But because Jupiter spins every 10 hours, it's fatter at the equator than the poles. So if you think of something spinning around, it bulges out at the equator. And so the net result of that is to make the orbit change over time. This is orbit 1 up here. By orbit 30, it's tilted, and we're heading towards orbit 70. So eventually we will go through these radiation belts. So that's the plan. And the idea is by getting up close, we can work out what's it like inside Jupiter. Do we have what the textbooks tend to show? Picture on the left, diagram on the left, where you have layers of a core of ices and rock and metal on the inside. And then you have a layer of metallic hydrogen, layer of molecular hydrogen, layer of gases on the outside. Or, as shown on the right, is it that things are all mixed up inside? So this is important for trying to understand how Jupiter formed and evolved with time. So the way we measure the gravity and the mass inside is to send radio signals back to the Earth as the spacecraft orbits Jupiter. And then we measure slight shifts in the frequency that tells us how much the spacecraft wiggles around that simple orbit. And that degree of wiggling gives us a sense of the mass inside. What is the distribution of mass inside Jupiter? And we can measure that by using these extremely sensitive radio signals sent back to the Earth and detected with the Deep Space Network. We can also measure the magnetic field. And what's important about Jupiter's magnetic field is it's generated in not liquid iron like we have at Earth, but in hydrogen, which at larger pressures turns into a metallic material. So that is, instead of having tightly connected positively charged protons and negatively charged electrons, when you go to higher pressures, the positive and negative protons and electrons can move relative to each other. And so you can drive electrical currents. And once you can drive electrical currents and you have a spinning and you have convection, then these are the three things you need to have a dynamo. And at Jupiter, we have a big volume where these conditions are met, and we have a very strong magnetic field. But we really don't understand how this dynamo works. So the idea is to go in with Juno, fly close to the planet, measure the magnetic field, map it out, work out what it's like inside. We also want to work out where the water is in the atmosphere, what drives the winds, all of these things. And so we have instruments on board to do that. So let me just show you a fun picture. I was allowed to go down to Lockheed Martin in South Denver, and behind you, here I am all dressed up in the bunny suits that you have to wear if you go anywhere near a spacecraft that's being built. Engineers on the right are putting together the spacecraft, and you can see that this is a big spacecraft. And in fact, that big white square behind my head, that's one of the microwave instruments. And then all of the electronics buried inside so they don't get too badly affected by the radiation are inside, and these engineers are connecting up and making it all work. The spacecraft was completed and ready for launch. We shipped it out to Florida. We slapped some stickers onto the top of the rocket. We took a selfie, and this is the science team at the bottom. And then we launched it. And we had a launch in August of 2011. And then it went out, didn't have enough oomph to get all the way out to Jupiter. So we had to do a flyby, come back and fly past Earth, get a kick, gravity kick, and then went out and arrived at Jupiter. And it says here, the 5th of July, 2016, but of course, in Pasadena, it was July 4th, and we were celebrating like crazy. Orbit insertion on July 4th. Fantastic. So we approached Jupiter and put it into orbit, and we have these large orbits, 53-day orbits. And since orbit insertion, we've had 40 flybys of Jupiter. The last one was just a couple of weeks ago, and we're great, very successful, great observations. And I'll show you a little bit about what we've been seeing. Well, the first thing is to realize that from the gravity measurements, we actually found out that instead of this simple core structure, a lot of the materials, heavy elements for the deep interior, seem to be spread and mixed up with hydrogen. And so it's much more diffuse, less simple textbook view of different layers. It's more mixed in. The other thing we did was to try and work out what's going on with the cloud structure. So if you look at Jupiter in infrared light, you can look a little deeper. You can actually look below the ammonia cloud. And this picture on the right is a movie that shows you the east and west flows. But you can see, this is Jupiter spinning, but you can see the belts and zones. And where it's dark is where you're seeing the cold upper layers of the white bands, if you like, the zones. And the bright regions in infrared are the areas that are red in the visible light. And those are deeper down and they're hotter, hence they're glowing more in the infrared. And so we get a sense of the depth and the sense of the structure deeper down looking in infrared. But if you look on the left of this diagram, you can see that if you use microwaves, the microwave instrument that has 6 different wavelengths from 1.37 to 50 centimeters. So 50 centimeters is half a meter, that's about 1.5 feet, sort of wavelength range. You penetrate a lot deeper into the planet and get a sense of the structure and the motions deeper inside. So we've been looking with a microwave instrument at the structure deeper and down, and we can go down to about 350 kilometers, and that gives us a sense of the deep circulation. So here we have maps with depth shown vertically and latitudes shown horizontally, and the colors give you a sense of the concentrations of ammonia. And you can see this is not uniform. It's not the simple multi-layered structure that you see in the textbooks. You have this stuff mixing up. It's more complicated. We've got a lot more structure. So it's not as simple as the textbook view here. And indeed, the belts and zones are probably similar to the Earth's belts and zones, but there's more of them, and they are actually probably going a lot deeper. And what's interesting is that this is telling us about the dynamics more dominated by rotation and turbulence than the effects of clouds and condensation, which is important for the Earth's atmosphere. So let's think a little bit about what we see in visible light. Yep, we carried a visible camera, take some snaps for the public. Okay, we'll do it. And wow, what has been so cool are these pictures. Now, what's interesting is this has been carried out as a citizen science project. So it's been involving the public from day one, and you can go look, just Google Mission Juno or Juno Cam, and you'll come up with these fabulous pictures, and you can download the pictures that were taken yesterday and play with them as you wish. So here are some lovely pictures. But what's interesting is that if you look the top left, it's the true color is pretty bland and you really can't see a whole load of structure. But if you crank up the contrast a little bit, the color, you can begin to see structures on the planet. And so here's an example where citizen scientists have taken the images taken by Juno and played with the contrast and the color to exaggerate the structures and really revealing the dynamics of what's going on inside. We have a rapid flyby, so we go 2 hours from pole to pole, so we're moving really fast, not able to stop and stare and take movies, but we get these amazing snapshots of the dynamics at Jupiter. And you can just crank up that color if you want and get some pictures like this, or you can crank up the contrast and get some pictures like this. And you can just play around with it, do some art. Why not? Van Gogh-like dynamics of the atmosphere. This is fun. This is great. A really fantastic experiment to make the data immediately available to everybody around the world to explore and do their own creative thing. And the citizen scientists have also been doing atmospheric dynamics, looking at the dynamics of the atmosphere, exploring it, measuring it, trying to understand what's going on. Here are some beautiful pictures. I'm just going to show you some of these fabulous images of Jupiter's atmosphere, highly turbulent, a lot of dynamical behavior. We're seeing these interactions between the belts and zones. We're seeing cloud structures that are sticking up. And if you, again, you show these contrasts, when you exaggerate the contrast a little bit, you begin to see these really dynamic features. What's interesting is that if you look at these white clouds, the first time we've seen these with Juno, are sort of popping up above the surrounding background clouds. These seem to be fresh clouds that are just coming up. And I took this picture out of the window of an airplane on my flight back from DC to Denver or something like that. And you can see here in Colorado, we have these pop-up clouds just like we have at Jupiter, but these are water clouds. And I just want you to think about what it would look like on Jupiter, where these are just, instead of water clouds caused by heating from below rising up and fresh clouds, you have ammonia clouds that are popping up above the cloud background. Here's a lovely example here. You can see these pop-up clouds here. And when you look closer to the terminator, you can actually see the shadows that give us some sense of the height of these clouds. Here's another example showing you the pop-up clouds to the right merging in. Some more really cool pictures, dynamics that people are looking at. Here's actually a little movie made by a short collection of pictures. We can see these really beautiful mixtures of the colorant, the red material with these fresh white clouds. And then again, this is an example where you look in the details of the turbulent, very turbulent atmosphere at Jupiter. Now, people have been looking at the atmosphere and seeing things in the atmosphere clouds, you know, since the beginning of humanity here on Earth. But at Jupiter, I love this picture because I just love the owly eyes over here, right? Isn't that cool? Of course, it was gone the next time, but you know, it's fun to see these things. And then here's Danny the dolphin. Look, here's the dolphin. And then behind there seems to be a dragon and then maybe a pelican over here. And yeah, it's just fun. It's just fun. And here's a bowling ball. Look at the 3 fingers, right? Want to bowl this out, knock out Saturn on the way. Okay, now what's cool scientifically is that Juno got the first views of the polar regions of Jupiter. And on the left is a visible, this is a put together several pictures, but you can see in the polar regions, unlike the sort of yellowy regions, orangey, reddy colors near the equator, with the poles, it's bluer. And that's the same physics that causes the blue scattering in the Earth's atmosphere to make the Earth's atmosphere blue. Scattering of sunlight up near the polar regions. But on the right, which is really interesting, we're looking at infrared light, and the north is North Pole at the top and the South Pole below. And you can see there are these circumpolar cyclones, these eddies around a central cyclone. And to the north, there are 8 of them. And to the south, there are 5 of them. And over the past 3 years, we've seen it's the same number of these cyclones, and this is the south, but orbit by orbit, we're seeing a few changes, and sometimes you see little eddies trying to come in, but they often get kicked out. Sometimes they're absorbed by the larger eddies. Here's one trying to come in. They get absorbed, as in this case, or they get kicked out, spat out again. And so there's something about the dynamics of the atmosphere and the South Pole that makes 5 eddies of these vortices, these cyclones. In the north, there's 8. And this has really got the scientists thinking about what's going on. If you look at Saturn, as we did with Cassini, Saturn, you have to remember, is 1/3 the mass of Jupiter, and the clouds are much deeper. And the wind flows are a little different. And so there's something going on whereby we get this central cyclone at Saturn, and then we have a hexagon around. We don't have 5 or 8 different cyclones. We have a hexagon. And so there's something different. And this is what the atmospheric scientists are struggling with. What is it about the mass, the flow speeds, the depth of the atmosphere that makes a different system at Saturn than it does at Jupiter? They're about the same actual physical size, just different in mass. Now, what's really interesting is in the past 6 months, some oceanographic scientists, oceanographers, have been looking at the Jupiter images and saying, wait a minute, what you're seeing at Jupiter looks very similar to what we're seeing in the sea. And for example, Leah Siegelman has been showing, she's at the Scripps Institute of Oceanography and presented these results at a recent meeting, saying if you combine rotation, turbulence, and convection, you end up with these sort of structures like we see here at the sea. Now, this is algae revealing the dynamics of the ocean flows. This is in the Baltics. But if you compare it with what we're seeing at Jupiter, so this movie sort of shows you how you can go from the sea on Earth to Jupiter, Jupiter's clouds, you see very similar structures where you have, this is a pair, a dipole with a cyclone and cyclone next to each other. And you can see that they're very similar structures to the ocean. And indeed, many of the atmospheric scientists who've been studying Jupiter have been saying, yes, this importance of rotation, importance of turbulence and convection, not so much cloud structure, is what controls the dynamics. So it's really interesting that by comparing Earth and Jupiter, we're beginning to understand the fluid dynamics of these different features and comparing them under different environments. Okay, to finish up, I have one more thing I need to tell you about. The Great Red Spot. So this is a Hubble picture, and you can see beautiful Great Red Spot. I think the color's a little exaggerated, but you get the idea. You know the Great Red Spot. This is a Voyager movie taken, Voyager 2, 1979, over several days. It's a 6-day circulation. Voyager was able to stare at the Great Red Spot and make this movie, and you can see it's about twice the size of Earth. And this is in fact a high pressure region with circulation around. What did Voyager find? What did Juno find? Well, this is what the artists think Juno found. Well, maybe not so much, but anyway, what Juno did find scientifically, rather than science fictionally, was that the Great Red Spot's been shrinking. It's smaller. It's 1.5 times the size of the Earth. It seems to be getting rounder, and it seems to be flowing a little faster. So the Great Red Spot has been changing. Juno also shows these beautiful eddies in the downstream of the Great Red Spot, showing the turbulence that's produced by shears of the flows in the atmosphere of Jupiter. So these JunoCam images have been combined with ground-based observations. This again is a combination of citizen science, ground-based scientists, amateur astronomers putting together their data with space-based observations to try and explore what are the dynamics and how are they varying with time. We've been able to map with the infrared and the microwave the Great Red Spot and finding that it's a lot deeper than we thought it was. So this is a deep, this is a deep structure, and it has been varying with time. Now, I gave I've given a couple of public talks on this topic, and you can go look on YouTube, focusing on the Great Red Spot and the dynamics of the Great Red Spot. So if you want to see what we're thinking about, and in fact, it's evolved since I did this public talk, what's happening with the Great Red Spot, or we can talk a bit about it afterwards. So I just want to show you these really, a couple more cute, cool pictures. Isn't this just fantastic? You know, this is a public outreach camera. We just thought it would take a few dozen pictures and then we'd be done, but no, it's just really extraordinary, this detailed structure that we're seeing in the atmosphere of Jupiter, and teaching us all about the dynamics of this giant planet. And here is the infrared picture showing you a movie of the infrared images taken with the GIRAM instrument. And you can see here the turbulence at mid latitudes, and then the series of 5 cyclones around the central South Pole cyclone. So I think you'll agree these are fabulous pictures and data that we're getting. Just show you, this is the Great Red Spot. Let me just finish. The last thing I wanted to mention is that we just got authorized to extend the mission to 76 orbits through September of 25. I hope the spacecraft can survive that long. What happens is, as the orbit changes from the first orbit through to orbit 75, is that we begin to cross the plane where the planets are. Before the earlier orbits, we went nowhere near the satellites, Io, Europa, and Ganymede. And we've now just had a flyby of Ganymede. We're soon going to do a flyby of Europa, and then eventually of Io, as well as going past the rings. And so we hope to do some satellite science, as well as measurements of the atmosphere, the interior, and the magnetic environment around Jupiter. And so that's what we hope for the next part of the mission. And I'll just leave you with this recent picture that was taken in June of last year of Ganymede, and you can see beautiful high resolution image of the surface of Ganymede. This is the largest moon in our solar system, has its own magnetic field, and you can see the impact craters and the geological structures on the surface of this amazing moon. And with that, I will just say that Juno is looking at the surface, the clouds. It's looking through the clouds into the deep interior, trying to understand the structure, measuring the magnetic field and the dynamics of the magnetic field environment. And actually, to be honest, the one thing we've learned is that this diagram is probably wrong. It's not as simple as this early cartoon of Jupiter, much more fuzzier inside and mixed up. And with that, I'll say thank you very much, and I'll take questions.
All right, fabulous. So let me give everyone the opportunity to unmute themselves, and we can go ahead and take questions. So fire away. Who wants to go first?
I have a question. On the Voyager, has Voyager hit the Oort cloud yet?
Oh no, not yet. No.
Okay.
It's got a long way to go to get to the Oort cloud. It's out of the solar wind influence, the sun's influence, out of the solar wind into interplanetary, interstellar medium. But the Oort cloud is much, much further. So we're talking hundreds to thousands of astronomical units, and it's at about 120, 130 right now.
Okay, thank you.
Because of the large mass of Jupiter, has general relativity been factored in or need to be factored into the signals that are coming back?
Now, we don't need to for doing the gravity measurements, actually, but there is discussion about whether or not we could we could use the radio signals to test theories of general relativity. That's a good question. I know that was the case in terms of radio signals from Mars going close to the sun, to the Earth, okay? And this was done back in the 70s and 80s. And they did test the theories of general relativity. But that was when the radio signal was going past the sun. And the sun is what, about 20 times the mass of Jupiter? And so we're not detecting signals that are going close enough to Jupiter to tell us, right? Now, if we do, as we propose to do, an extended mission, radio occultations of the atmosphere of Jupiter, so sending signals from behind Jupiter through the atmosphere.
Oh, yes.
Right?
Yeah.
Then
Right.
we would need to include general relativity. Excellent question.
Who's next?
I have a question.
Go ahead, Kara.
I don't understand, being that I've lived all my life on a terrestrial planet. If there's a gaseous planet, what do you mean by the surface?
There is no surface. I should not have used that word. I'm sorry.
No.
There is
People
no
use it
surface.
all the time. So if you were to crash a satellite into Jupiter, it wouldn't hit anything, right? It would just, from the pressures,
It would
would
burn
just
up. It would burn up.
explode.
Yeah, it just burn up.
So is there an atmosphere then? I mean,
Yeah,
what
there's
do
an
you-
atmosphere, very thick atmosphere of mostly hydrogen, some helium,
above the what?
and then you go down, and what happens is you go from molecular hydrogen above, it becomes like a fluid deeper down. And then once you get deep enough, about 80% of the radius, that hydrogen turns into metallic hydrogen. That is plasma, where the electrons and the protons move separately. That's what I mean. That's where the magnetic field is. But the pressures are quite high. And so if you think of the atmosphere pressure here is about 1 bar. It's called 1 bar, and we use that unit because that's what we breathe, right?
Mhm.
But if you go down to where hydrogen turns into metallic hydrogen, it's at about 2.3 million bars. Million. Okay? And the center of Jupiter, it's about 50 million bars.
Mhm.
So the pressures are really high. It's a little hard for us to imagine those high pressures, but the gas changes in behavior once you get to really deep
Mhm.
pressures.
So if you're bouncing like radio waves off Jupiter, does it, is it a little spongy or is it solid at a certain point?
It's still a fluid as you go deeper down.
Mhm.
This is a big debate as to whether it actually is solid at those very high pressures in the deep interior.
Mhm.
And they're still trying to work out. So you may remember from your college physics or high school physics, there's this term equation of state, which describes the pressure, temperature, and density of a gas, right? And we often use the term ideal gas. How does an ideal gas behave? It's just typical physicist sort of, how does an ideal gas behave? Well, that's all very well with the pressures that we experience here on Earth, but the pressures deep inside Jupiter, we don't know how those gases behave because we don't have experiments that can go to such pressures, even in the most sophisticated labs on Earth.
Mhm.
And the theories, the quantum mechanical theories, they're arguing about it. They don't really know how hydrogen, the most abundant element in the universe, behaves at these pressures. Okay, so we're trying to work this out,
Mhm.
and that's what Juno is helping with.
Well, thank you.
Any other questions? I noticed you didn't mention the Galileo mission too much.
Right.
If you had to mention just a few highlights of the mission, what were some of the major findings of the Galileo mission? I know, but I figured you would share it with everyone.
Ganymede has a magnetic field.
That's one, yeah.
Yeah, totally cool. Ganymede has a magnetic field, and we've flown through it with Juno just this past summer. And then there's a new mission that the Europeans are going to send to Jupiter. They're building it now, and I think they're going to launch it in a couple of years, and it will get there about 2030, 31 or something like that. It's called JUICE, and it's going to go in orbit around Ganymede, which will be totally cool. It'll measure the magnetic field. It'll look at the ice, look at the atmosphere, look at everything that's going on, and the interaction of the environment around Ganymede with that magnetic field. So that's one thing. Galileo detected this magnetic field. It got us all excited about, you know, why is it that Ganymede has a magnetic field? The other thing that we found is that Europa, so Io, Europa, Ganymede, Callisto. Europa, which is the smallest of the 4 Galilean moons, has a rocky interior and a thick layer of ice on the outside. But we also know that under the top layer of ice is a big ocean of water. And we know this because when we flew by, we measured a magnetic field that has indicated that you have an electrical conductor inside. Now, metal can be conducting. Rock is not very conducting, electrically conducting. Ice is not electrically conducting, but water is, if you have some minor amounts of stuff like we have salt in the salty ocean of the earth, right? So oceans are known to be electrically conducting. So if we measure the electrical currents that are induced in this ocean by flying by and measuring the magnetic field, it tells us Europa has an ocean.
Would that be?
Yeah, what was the question?
Would that be true of Ganymede also, with a liquid core?
The liquid core inside Ganymede that produces the magnetic field is probably iron. Okay, so the magnetic field is probably produced in iron in the deep interior of Ganymede. There is likely, there's good evidence, there's a bit of an ocean inside Ganymede, but it's very, very deep and thin. The difference with Europa is not only is it a large volume of ocean, many times the volume of Earth's ocean, and I don't know the number, so I'm not going to quote it, but it's a large ocean. And then you've got thin layer of ice on top. So that thin layer of ice on top protects the water from the radiation, the energetic particles that are bombarded. But it's beneath that in the ocean, it's warm, it's been around for a long time, it's liquid, it's got material that we think is coming out of vents deep inside. This is just like the deep oceans of the earth where we know life is generated, okay? You have heat, you have liquid water, you have minerals, you can make life. And so we think that, many of us think, if you want to go find life, Europa's ocean is the place to go, okay?
What's the source of heat to keep the water?
So Io, Europa, and Ganymede are in this really strange orbit around Jupiter. And, you know, Galileo found this, right? What you find is that for once that Ganymede goes around Jupiter, Europa goes around twice and Io goes around 4 times. And so there's a tidal interaction between these moons. And what happens is that tidal interaction leads to heating. And with Io, the innermost of these 4, it is really heated. So think of it being squeezed and pulled, and it is covered in volcanoes. These volcanic eruptions are caused. There's about 200 active volcanoes on Io at any one time, okay? And all the water has been removed because it's too hot and driven off all the water. Then you go to Europa, And yes, it's had some tides, a bit of this tide, but not as much as Io. And so what that's done is it's driven off a lot of the water, but not all of it. And now you have a source of heat, which is the tidal heating of the rock that's underneath the ocean, driving material out into the ocean, heating up, and also venting out materials that then provide minerals and stuff to the ocean. And so it's just prime for producing life. Just as the hot vents in the Earth's ocean, you know, the black smokers, if you like, or whatever you want to call them, volcanic regions that vent out into the ocean on Earth are generating life forms on Earth. And so that's why we think this is the most likely place that there's life in our solar system other than Earth. And there's a mission, the Europa Clipper mission, a NASA mission, that will go and fly over Europa and make measurements, look for hot spots where there may be connections between the ocean and the surface. There may be venting regions where water and materials come from below, coming out. That brown streaks we see on Europa could well be debris from these venting places. There's a lot of possibilities, and if you're interested in astrobiology, Europa is the place to go. And so the Europa mission will get and do these multiple flybys of Europa in, again, launching in a couple of years, getting there around 2030 or so, and making measurements of Europa, which will be really cool.
Will they be looking for organic molecules?
Of course, they will be looking for prebiotic chemicals and organic materials that are produced inside and coming out onto the surface. You do see these brown stuff. It seems to be brown gunk, as we call it. Well,
right.
Technical term.
The organic.
Coming out of these areas where there's sort of cracks in the ice. And so that would be the obvious place to go look. And if you could do a sample, scratch and sniff the surface, that would be the place to go and see if you can see organic material. That would be a really good place to go and look at it. There are spectroscopic ways of looking. It's actually really hard spectroscopy to measure organic material, small amounts of organic material in the ice, because the signals get sort of buried by the ice signals. But we think we have ways we can go and see what's there and work it out. And then follow it up after a flyby with multiple measurements, looking for heat, looking for the right place to go and land. Then we can go and land and scratch and sniff the surface with a lander and do chemical analysis. Yeah.
Thank you.
One more comment about the life at these vents. The ones on Earth, the creatures that live there couldn't live nowhere else. And they thrive in it, what we would consider a poisonous situation.
Right. So we have no idea what kind of life forms we might find. It's probably not going to be charismatic megafauna like whales. Pretty unlikely, but one can hope. More likely we'll find bacteria, and indeed it's very likely that any of this material that forms near these hot vents, once it gets up anywhere near the surface and out onto the surface, will likely die off. But even if we can measure extinct material, it'll give us a really good sense of what's there and what could be deeper down underneath. Yeah.
Thank you.
Sure.
We still got time for a few more questions if anybody has any.
Yes, go ahead. Go ahead.
I was just curious what you might think we would find. What would, no, wrong question. What would you like to find?
Well, I am not, I'm not overly, what's the right word? I'm a bit of a realist. I don't think we're going to find anything, like I said, I don't think we're going to find charismatic megafauna. What we're going to find are bacteria. And the real question is, how does life form? We don't know how life forms on Earth. And would life form in a different way on Europa? This is a fascinating question, right? The fundamentals of how life forms Is it the same? You know, do you have the same structures, the same DNA on Europa that we do on Earth? I find that very unlikely, but maybe there's a reason why the chemical pathway goes this way, and that's the way you make life. Or are there multiple pathways? I would suspect there is. Chemistry tends to be multiplicity, and then different conditions will lead to different life forms. You know, that's what I would guess. But I don't know. I'm not a biologist. I could be totally wrong. But I hope to find some hints of whether or not life formed, evolved separately from Earth. There are those that say, okay, but maybe life formed from Europa landed on Earth, or life formed from somewhere else. You know, maybe a comet landed on Earth and landed on Europa, and it comes from elsewhere. I'm not so sure. I think that the chances of that are so extremely slim. It's very unlikely. Personally, I think it's more likely that they will evolve separately on Europa and on Earth, and comparing them would be extremely interesting.
Did you see the movie Europa Report, where they land on Europa? Yeah.
No, we don't talk about our Europa report.
It's a little, let me just say, optimistic or
Yes.
exaggerated or out of. Anyway, I think real science is fascinating and extraordinary and mind-blowing enough as it is.
Oh, sure.
We don't need to invent.
You had mentioned earlier in the talk that the instrumentation, everything gets locked down at the time the mission is approved, and I have seen a video recently that kind of shows that, whereas it took 6 years to test even the solar sail, not the sail, but the solar protector for the JWST. But in this day and age of computer administration and better optics, can we put a better camera and computer on these satellites before they are launched, instead of clocking it down 10 years before they're launched?
So this is a very good question, and it's something that we struggle with every day when we're writing proposals or evaluating proposals at NASA for missions, future missions, and so on and so forth. The answer is that once you send a spacecraft out there, and once you move beyond Hubble, you go out to JWST or out to Pluto and so on. Once it's gone, it's gone. Mm-hmm. And you're going to invest a huge amount of energy, not to say money, in making this spacecraft. The reliability is more important than taking a risk of risky technology. So yes, inevitably, we have these technology readiness levels. And in order for something to be selected for flight, it's got to have reached a sufficient technology readiness level that we're confident that it will work. And so, yes, there may be some new shiny technology that you say this could do it better, but until it's tested, we really can't fly it, right? Now, there are ways using small sats in orbit around the Earth, using rockets, balloons, things like that, where you can test a technology and move it up this technology readiness ladder to the point where it's ready to go on to a very expensive spacecraft. Or if you have the resources, and this is, mass of a spacecraft is really a critical factor. But if you could afford a little extra mass to take a small miniaturized instrument and fly it as a test instrument on a regular spacecraft that's got an objective with tested instruments and so on, then there are ways in which you can test out these things and move them up, accelerate that motion up the technology readiness ladder so that you can fly them sooner rather than later. But unfortunately, I mean, the reality is that it takes time. And yes, technology goes rapidly. But I like the miniaturization has been amazing, and the low power, high data rate, lots of data processing, storage, and lightweight capability is extraordinary. How that's changed space, and it's the reason why I believe, and I'm going to go out on a limb here, I believe there's nothing that humans can do that robots can't do cheaper, better, or more efficiently, except tourism. And I don't believe taxpayers should pay for tourism. Now, when you go back to Apollo, which I watched as a child, no, we didn't have the technology. Humans were the best robot that we had. Now we have robots that can do so much more, right? And I'm not just talking about the dancing dogs, or, you know, you watch on YouTube, you can see these things. You know, there's lots of things we can do with spacecraft, lightweight technology, high data rate, onboard data processing, storage, data compression. Those are the things we should be doing. And they allow us to do all sorts of amazing things like JWST.
Thank you very much.
That's not exactly miniature or lightweight, I know, but you know.
Fran, I had a question. What do you see coming up in space exploration? I think you were hinting maybe what might be coming up, or what you would like to see coming up.
So I love your background picture, of course, my favorite picture. So
I just downloaded it.
It's fantastic, isn't it? Let me say there's a couple of things that I think we need to do. Number one is, I think we need to go to Uranus or Neptune. Uranus is easier than Neptune. We need to do that. We need to go back. Voyager did a flyby of Uranus, a flyby of Neptune, that's it. We need to go back and look at those giants, because they're different from Jupiter and Saturn. They're much smaller, they have a lot more water, they have a lot more methane, that's why they're blue. I think their dynamics and the formation and so on and so forth of those are very important. So I would argue for a mission to Uranus or Neptune, probably Uranus. Second thing I would really strongly argue for is a mission to Venus. Now, I don't have a stake in that. Venus does not have a magnetic field. It does not have a magnetosphere. I don't have any science that's my science at Venus. I'm advocating for Venus because it's our sister planet. It's next door. It's the same size as Earth. It does not have a magnetic field. Why? It has this strange geology where the whole surface 600 million years ago turned over, completely resurfaced it. Why? It has this atmosphere that is thick, dense, toxic. Talk about climate change. Oh my golly gosh, and greenhouse gases. Venus is the place to go and look and understand. Why is it we're not exploring our sister planet that's right next door? Well, I think it's because everyone wants to go to Mars, which is easy by comparison. And they're being, well, okay, let's not don't get me wound up about Mars and wasting money on Mars.
Thank you.
So I know that Titan, like, it helps make Saturn's rings. Do you think Europa, because of the water on it, would help Jupiter form rings?
So I think the rings are formed when you have a moon that gets a bit too close to the planet and breaks up. So I don't really think that the Galilean moons have much of an influence on the rings, to be really honest with you. There is some tidal interactions maybe and some gravitational effects, but really what you need is to have a moon that gets broken up close to the planet that makes the rings. So there may be some structure in the rings that are affected by Europa and Io, Ganymede, but I don't see them forming the rings. They may be involved.
You wouldn't want me to have this there.
You talking about the rings of Saturn or Jupiter?
Jupiter, for
Jupiter. Okay.
for Saturn, there is some argument this giant moon Titan maybe have been involved, but I think that and you can see from the picture that's behind your head, there are these structures in the rings, but my understanding is that those are probably largely formed by nearby moons, causing resonances and these structures, rather than the further out moons that have less of an influence. Yeah.
Any other questions? It sounds like the answer is no. So I want to thank you, Dr. Bagenal, for joining us. It was great to see you again. It's only been, gosh, how long has it been now? Almost 5 years? Of course, you didn't see me, but I saw you. I could even show you the pictures if we had time. We don't have time. So again, it was great to have you as a guest speaker. It was a little overdue, and that was fabulous. I really enjoyed it.
I look forward to meeting you again at the next eclipse.
Absolutely. Before we move on, I just wanted to mention, since we still have several people here and some of you might be skipping out, is we got some pretty great presentations coming up. Of course, for our April meeting, and I'll put the registration link in the chat there, we have Dr. Melissa Trainer from the NASA Goddard Space Flight Center. She'll be talking about flights of exploration of an exotic ocean world. And so speaking of Titan, she'll be speaking about the Dragonfly mission to Titan. So that's going to be one of the really exciting missions coming up here in the future, because I know Dr. Bagenal loves Pluto,
yeah.
but
no.
Titan's much better.
Amazing. Dragonfly's amazing.
Oh,
we
yeah.
just had a seminar at CU from the head of Dragonfly, which is Zibby Turtle. Amazing mission. It's going to be totally cool. You'll love this presentation.
Yes. And then for our May meeting, let me put that in the, I'll put the registration link in the chat there. We got a very special gift for the membership. We're going to have Dr. Alex Filipenko, one of the world's foremost cosmologists from UC Berkeley, who will be giving a presentation called A New Surprise in the Accelerating Universe. And so even though most of you paid your dues, we should probably charge extra membership for that because it's so cool, but we won't. I could go on. We got one more great speaker in June, but I won't mention that because it's so far away. But we definitely have some excellent presentations coming up, because we've been taking full advantage of this Zoom format and bringing in some fantastic speakers. So everyone is welcome to join us. So I just want to again thank Dr. Bagenal. I think she may have bailed. Oh no, she's still here. So just want to thank you for joining us. If you have to skip out early, but you're certainly welcome to stay. So long, or thank you.
Thank you.
This was awesome. Thanks so much.
Yes,
Very
very,
welcome.
very, very interesting. Thank you, Doctor.
All right, let's keep a moving here. Let's begin with the president's report. But
hold on,
actually,
Richard,
yes.
let me jump in just for a second. My
go ahead.
students who have attended, you don't have to stay for this part of the meeting. This is more about technical stuff that the club itself is doing. So thanks for joining. I got your names. You're all set. Thanks, Richard.
Oh, you should stay though. It's kind of rude to leave now. Okay, so first up, before we actually get to the president's report, we have another awards presentation. So Aaron Roman, our Alcor, bagged another one. He has successfully completed the Astronomical League's Double Star Award, which is my favorite observing program. So Aaron, let me highlight you here, or spotlight you, whatever they call it, and you can show us your pin and certificate.
Well, I know I'm not the only one working on the Double Star program, and I know that I'm not the only one who's completed it historically too, so but there's the certificate, and see if I can show the pin.
That's it.
Little double stars.
Ooh.
Sweet. I think I'm the third or fourth person to finish it though, so that's kind of cool.
I'm happy to report, I'm pretty sure I was the first in the club to do that one.
Yeah, Christian, you were the first, and I think I was the second. I think Mark
No,
Miller was
Mike's
number
got it.
3.
Yep.
Yeah, I think Mark Miller was number 3.
Out of the 5 or so I've done, that was my favorite because it was, it was not deep sky objects, although I kind of consider binary stars deep sky objects. They're kind of deep sky objects, but it was different. It wasn't star clusters and nebula galaxies, it's double stars, and that's kind of what really got me going in astronomy, thanks to the setting suns and Star Wars and that sort of thing.
Well, the biggest difference is that you have to sketch their angle and separation, and it really forces you to observe. The other ones you can kind of get in there and any observation's good enough, but with a double star program, you need to be a little bit more on your game and pay closer attention and have a better understanding of your equipment, and it just ups your game a little bit.
All right, so good job, Aaron. How many is that for you now?
I think I'm up to 6.
Wow, okay. The L Corps should have the most. That just seems right. All right, so let's move on with the president's report here. It's very short, thankfully, so please hold your applause. We talked about last month how we might hold a planning meeting to travel somewhere, preferably in Texas, for the 2024 eclipse. I just wanted to mention I'm still thinking about that. I'm kind of waiting to get the lecture series over with because that occupies a lot of time, that and the newsletter and all that sort of thing. So I'm still working on that, and hopefully we'll do our first meeting about where to go for the eclipse, probably in mid-March or so. Everything should be kind of settling down by then. And again, this is for people that want to maybe travel to Texas. And I'm sure some of you are going to try to stay close to home, but this is for those of us that actually want to see it and go to where the clear skies will be plentiful. And that's southern Texas, like west of San Antonio. If you didn't read the newsletter, and of course many of you have not, we've decided to hold the Perseid Potluck Picnic at Van Buren State Park on August 13th. We have the reservation site reserved thanks to Anna. But the bad news is they are not allowing us to stay after sunset, at least not officially, to observe or photograph the sunset. So if we do stay after to observe the sunset, we'll have to, move outside the gate, or I think my plan would be just to drive over to the South Haven Pier and go there instead, because they're not too far apart. So that's where we are with the picnic, and I probably won't mention that again until at least June. So we're all set there, and hopefully at least some of you here received your membership cards in the mail recently, because I mailed out 20 more of those things this past Monday, which is February 28th, and you should have got those in the mail. And I'm pretty much caught up on membership cards, with maybe a couple of people that either joined very recently or renewed. And if you do have an expired membership, tomorrow's the day that I purge the membership. So it looks like I'll be purging about another 25 people. Well, not 25 people. So we'll probably end up losing about 35 members or so, which is a little more than usual, but the club's way bigger than it has been in recent years. So that is it for the president's report. Is there any observing reports anybody wanted to share? We've had some clear skies.
I have a small observing report I'd like to share.
Oh, great. Hi, Karen.
Hi. So I got a pair of Lunt mini sinoculars for Christmas. And I have to admit, at first I was a little afraid of using them incorrectly, but I persevered. And so I've tried observing the sun 3 times with them. And the first thing I noticed is that I have a lot of trees around my house, because the sun looks like a small orange circle with delightful tree branches in it. So I need to find a better place to do it. But it's really been interesting. I've looked through them 3 times now when the sun was at different places in the sky. And I'd be interested in finding out if anyone else has ever used the mini sinoculars and has any tips.
Yeah, I have the larger pair, the black ones, which I actually didn't have to pay for. I actually won them from Lunt, which was really cool. And the first thing that I discovered was it's really hard to find the sun with those at first. You'd be amazed. You think, oh, it's really, of course, the sun's the brightest thing in the sky with binoculars or sinoculars. It's really easy to find. It is not that easy. Do you have the larger pair or the smaller pair?
No, they're the smaller pair, the little mini ones. I have them right here.
Okay. Oh, the red ones.
So,
okay.
Yeah. So one of the things about this is that you can adjust the eyepieces individually. And when I wear my contacts, I have one that's for close vision and one that's for far away vision. So I don't have to have bifocals. So that was why I thought that would be helpful. But the sun's not very big in these, and smaller than I expected. And I was kind of wondering if part of that is because it's the winter, and when I've seen the sun before, it's the summer, or maybe it's just the magnification is very small.
It's just the magnification's small. By the way, everyone should own a pair of those sinoculars. They're only like $25. They're really cheap.
So what are they?
They're basically binoculars you use to look at the sun. So that's why they call them sinoculars. That's all they can look at is the sun.
And they're just filtered on the inlet?
On the objective lenses,
yes.
Solar filter.
Okay.
Yeah, and if you try to look through them at anything but the sun, it's just completely black, which is what it should be.
Yep, you would hope so.
They show a white light. They show a white light image of the sun.
Yes.
Okay.
Yeah, there's no such thing as H-alpha binoculars unless you put two H-alpha scopes together, which I'm sure somebody's done that.
Yeah, it looks very orange. It looks orange.
Yeah.
All right. Any other observing reports? It is an observing club, you can tell. So let's go ahead and move on to astronomical news.
I actually had a question.
Oh yeah, go ahead, Kevin.
Though I'm interested in those sinoculars. What's the eyepiece relief? Because I wear glasses.
So I use them when I've got my glasses on. I just take my glasses off and use them. I don't know what eyepiece relief means, but each of the eyepieces is individually adjustable for focus.
They're 6 by 30, right?
Yeah.
So they're probably 5 millimeter exit pupils.
Well, remember we talked about it in the binocular lecture series. That it's not the distance. Like people with glasses can go up to like 21 millimeters away or something. I can't remember what the wording is right now.
I think I'm talking about the eye relief rather than
eye relief.
Yeah.
On the Sinocular website for the red ones, it says the eye relief is 13.6 millimeters.
All right, thank you.
That's pretty doable.
Hopefully that means something to you.
And of course, if you want a pair of those, you should order them really, really soon, because once we get closer to 2023, they're going to be hard to get because of the annular eclipse and then the solar.
Yeah, well, I mean, if I look at the sun, I just go and throw my Thousand Oaks filter on my zoom lens.
There you go. All right, astronomical news. I have not heard a whole lot about the James Webb Space Telescope. Does anyone have any updates on that? Anything new?
They got a star that they got in. Well, they're starting to focus. It's interesting because you can see the different all the different mirrors and how they kind of interact with each other just by looking at the star image.
They've actually got to focus down to one image now. They're just doing final tweakings and things. But I did see online a report from JWST that they had combined all of the images into one.
Yeah. They're also calibrating its location to make sure they have it exactly where they were wanting to aim it. So they're trying to identify the one star, and they're trying to figure out what the angles are for each of those, so we can figure out exactly where it's at in the L2 position.
The last I saw, they're doing phasing of that. They explained that they have 18 telescopes all pointed at the same place, but acting like 18 independent ones. And to get the phasing done, they will begin for the first time to act as one mirror.
They should have just bought an Orion laser collimator. They'd be done by now.
Yeah, I saw the same report. I think they're saying 7 months in order to finish that part of it.
Yeah, I got an email from the Night Sky Network, who, they publish an article in their newsletter every month, and they were looking for proposals for events in July to debut the first image. And I was thinking, they only gave us like 3 days notice, and I was thinking July, that's impossible to get really anyone to do much anything. So I figured, we'll just watch it on the internet by ourselves. But who knows? Maybe something will develop, but I doubt it.
I think for that program, they're just saying whenever the first images are. Could be as early as July, might be October.
Yeah. Okay, more news. I was reading, this is kind of bad news, but I was reading Sky and Telescope today, and they had, of course, an article out up there on the impacts on space with the Putin war in Ukraine. And it sounds like that's going to wreak a lot of havoc on the International Space Station, because it sounds like the Russians might totally pull out of ISS by 2024, and we depend on their modules to boost the orbit once in a while. And the article wasn't specific, but it doesn't sound like NASA would have access to the Russian modules to boost the orbit. But we have Docker, probes that can do the same thing. There's certain probes, like I think the Cygnus probe or something like that, that could dock to the ISS and boost the orbit. And then the European rover might have to launch a little later than planned because they were going to launch on a Russian rocket, and now the Russians basically say no. But at least we're in a much better position than we were back in 2014 when they annexed Crimea, because with all the sanctions, the Russians were telling us that we'd have to get to the ISS via trampoline, and so that wasn't very good back then. But it's much better now, thanks to SpaceX and Blue Horizons and stuff like that.
Yeah,
So
but look, once they bail, if they bail the ISS, it's ours now. So
yeah,
let's lock them out. We can put a module up there. We can lock it into that location. We have all of the docking mechanisms are supposed to be standardized for this. So, have at it. Elon Musk says he can put a spacecraft up there and push it a little higher. It's a little off center, but hey, too bad. You want to play that game, you can play it back.
Yeah, Musk said he can use the Dragon craft to push it up.
I hear it really stinks up there. Your astronauts might be saying, I don't want to go up there anymore.
There was news today that the Russians government told the Russian astronauts not to work with the German astronauts on the International Space Station.
Oh, that makes me feel so sad inside. You see me feel sad? See the tears run down my face? There aren't any. I'm sorry.
I read somewhere.
That's the current crew is Russian, German, and American.
I'd read somewhere online, and I'd have to search to where I found it, that some of the parts we're going to be using for the engines for Antares and the Atlas V rockets come from Russia.
I don't know.
And they're going to stop giving us those parts. So that could affect those missions.
Yeah, the Sky and Telescope article talks about that. Some of the parts for some of the European rockets come from Ukraine. Of course, it's a little difficult to manufacture anything in Ukraine right now for fear of getting blown up. We almost had another Chernobyl yesterday. So that's a whole other topic.
Just buy the parts from China. They make them.
Yeah,
they got Tiangong up there. So you know what? We don't need to rely on the Russians.
Yep. Speaking of which, that's the next bit of astronomical news. Is it's supposed to happen today. A rocket booster is supposed to impact the far side of the moon. At first, they were saying it was a SpaceX rocket booster, but it sounds like now it might be from China's 2020 Chang'e 5 mission. So I don't know what time that was supposed to hit today, if it's happened already or what. So I have no idea.
I thought it was supposed to be like 7:30 in the morning Eastern time.
Yeah. Of course, it's on the far side, so it might take a while to figure it out.
I did see a little bit of a cloud burst when I was looking at the moon this morning, though. So that was probably it.
That's probably it, yeah. Any other astronomical news?
Can that lunar reconnaissance one monitor it?
It's pretty narrow field of view for something like that. So I'm not sure we'll ever know if the thing impacted at all, unless the only way we might know is suddenly we don't see the booster move around anymore. You know, it's suddenly gone.
Wait a minute. Moonfall.
Uh-oh.
Watch the movie.
God, no.
Oh no. That's terrible.
I was looking it up. It looks like it impacted at 12:25 GMT.
Okay.
So about 8:25 this morning.
Oh, so it's over.
Yep.
Very exciting.
There's been a lot of news, and there's a lot of things in the news about the Parker Solar Probe and about this very, very large galaxy. Have you seen that one?
No, I have not.
Okay. I'll have to find the article and send it to you.
Sure. All right. I don't believe there's any more astronomical news, so we'll move on here. Let me cover upcoming events. Tomorrow, we were originally supposed to have the Messier Marathon at Richland Township Park, but we've discovered that Richland Township Park is now closing their gate at night. We're not sure if that's a temporary thing for the winter or they'll start leaving it open once we get into spring and summer again, but we really don't know.
It should be open. He said he was confident he's going to open up in April.
Okay.
But we still got to fill out a permission slip, so we'll do that.
Okay, great. So instead of Richland Township Park, we were going to have a pre-spring stargaze at the Nature Center, even though technically I should have checked with them because they have the Maple Sugar Festival this weekend. But when I planned this just before the newsletter came out, I knew it wasn't going to happen just looking at the weather. And it's not going to be as rainy tomorrow, I don't think, as they thought, but it's going to be as cloudy. So I'm pretty much going to tell you the pre-spring stargaze for tomorrow is canceled right now. So we'll try again with the public observing sessions that begin on April 9th. And we have the final installment of the Introduction to Amateur Astronomy lecture series. Part 5 is called The Art of Astrophotography. And I might send out just the webinar link to the membership. You don't have to register. So if some of you just want to check out that lecture on astrophotography, that's fine. But I can give you a quick preview. You know, it's not about any one specific subject like we have at the SIG meetings, but it's a very broad introduction to astrophotography. I spend most of the time doing stuff or talking about stuff that anybody could do with a DSLR or mirrorless camera. And that is, you know, stationary tripod photography, you know, constellations, Milky Way, star trails, stuff like that. So I try to spend most of my time talking about things that anybody could do, but I will get into guided astrophotography with the portable tracking mounts that everyone loves to using today. We'll get into more wide field prime focus stuff, talking a little bit about some of the cameras available today. And then we'll end with planetary imaging and stuff like that. So it's a very broad view of all the basic types of astrophotography that you can do. And again, that's going to be on Saturday, March 12th at 1 o'clock. Of course, if you're registered, you'll definitely hear from me. But if not, I'll probably send out a little reminder about that. And, you know, things with the lecture series are going very well. We have over 1,120 that have registered. Which is more than 200 last year, but the attendance is really about the same. It was probably a little bit more for the first one this year than it was last year. You know, but I haven't kept detailed track of the attendance, but from my memory, they're very comparable to last year, which is great. Donations are going as well this year as they did last year, but Miller Planispheres this year are way above what we did last year. In fact, you know, normally years go by, like 2-3 years or more go by before we have to order Miller Planispheres. And I ordered some at the end of January and just picked up another order today. So we went through those pretty quick. So I have a whole new batch of those if you wanted one, but didn't speak up. So I very much doubt I'll sell out this time. And we're hoping to have our little graduation ceremony at the meeting next month. So the lecture series is going pretty well, but honestly, I'll be a little glad when it's over because it's not just giving the lecture. There's a lot more work involved, and I'm ready to get into spring and start observing again. We have another astrophotography SIG meeting on Friday, March 18th. And David Churchill, who has an observatory at Arizona Sky Village, will be talking about remote astro imaging for everyone. Of course, he does remote imaging with his equipment at Arizona Sky Village, but what we've kind of asked him to speak a little bit more on is the installment he and Fred Espenak, Mr. Eclipse, have in the Southern Hemisphere, because that's the type of dream imaging we wish we could all do, have a telescope in the Southern Hemisphere where you get a whole new sky. So that'll kind of be a talk, I think, for everyone. It shouldn't be terribly technical. So if you want to see the telescope in the Southern Hemisphere and see some of the targets he's imaged, you can check out the meeting on Friday, March 18th at 8 o'clock. And then we have a observing SIG session at Richland Township Park, assuming the gates are open, on Saturday, March 26th. Any reports about the SIG you want to give, Aaron?
We started diversifying our who's giving presentations and sending emails out, so it's our kind of our cloudy date constellation prize. So I'll be sending out one from probably in the next week or so.
Okay, great.
Sorry.
All right, moving on. Prime Focus, the usual deadline is the 15th of every month. And I just wanted to mention that 33.6% of the membership actually downloaded the newsletter this month. So that's a little better than usual, but still 33%. I mean, so come on. So if you haven't looked at the newsletter yet, you're breaking my heart. Download the newsletter and check it out. It's not a terribly long read. What do you people do when you're on the toilet? Don't you have like your phone or your iPad? That's perfect Prime Focus reading time. Yeah, there you go, Pete. Just read it on the phone.
I read it twice.
There you go. See,
that doesn't sound right, Richard. That just doesn't sound right.
And that's of course, that's when all the great thoughts occur to your head too. Usually for me, it's in the shower when you can't take notes or anything, but
maybe you need a crossword. Maybe you need an astronomy crossword puzzle then.
Well, you get working on that.
Yeah, Star Wordle.
Yeah, there you go. We'll become famous.
No, you need to find a word. Those will take longer.
Hey, I got a couple developers at work that are kind of bored right now, so
there you go. All right. Now we're to the other items on the agenda. Is there anything else anybody wanted to mention about the club or astronomy or your Swiss bank account number? Please send that to me. That'd be great. Hearing nothing, we'll move on. As mentioned, we have a great speaker next month, but just note we decided to delay the meeting 1 week because we were maybe hoping we could be at CAMSI, and maybe we still could, but I doubt it. But we're going to have our meeting on April 8th. So the second Friday in April, we're going to have flights of exploration on an exotic ocean world by Dr. Melissa Trainer. And so again, the Dragonfly mission to Titan is I think one of the most exciting missions we have on the board. And I'm personally really looking forward to that because, I've always been a big Mars nut when I was a kid, but boy, Titan really gives Mars a run for its money. It's way cooler than Pluto. I mean, Pluto just has that heart. The rest of it's pretty boring. So who cares about Pluto? Titan's much better. So I'm really looking forward to that. And if there's nothing else, we will go ahead and officially adjourn. So thanks for joining us, everybody.